Homework 2.7, inverse functions, video 2, homework due Friday, May 22nd, 2020 at 11:59 p.m. The following video will correlate to homeworks 1, 2, and 3. Homework questions 1, 2, and 3. So in the previous video, we established the definition of two functions being inverses. I've rewritten the 4 parts of the definition just to summarize them. When you do the composition, the result is just x, regardless of the order you do it in. And for either pair, for either function, its domain must match the range of the other. Domain of f equals the range of g, domain of g equals the range of f. So let's see if we can verify that a couple of functions are inverses. The two functions we have here are f of x equals 5x plus 7 and g of x equals x minus 7 over 5. Now, you may try to think yourself into saying yes they are or no they aren't, but the nice thing about verifying if functions are inverses is that you don't have to guess anything. You just have to check 4 things. 2 compositions and a pair of domains compared to a pair of ranges. I want to actually start with the, actually we'll do the domain and range last. Let's start with the compositions since they're listed first. So the first thing we have to do to verify or determine if these functions are inverses, if I were verifying, I would already know in advance that they are inverses. Right now we're determining, are they? We need to check g of f of x and see what that gives us. If you've forgotten how to do function composition, I refer you to the previous series of videos, specifically the last 2 questions, the last 2 videos. But for g of f of x, g of f of x literally means g of f of x. And although we can drag it out a little slower, there is a quicker way to set up a function composition. You write the outer function, but replace its x with parentheses. So since the outer function is g, I'm going to write this, but change the x to parentheses. So parentheses minus 7 in the top, 5 in the bottom. And then inside the parentheses, you write what the inner function equals. Since the inner function is f of x, and that equals 5x plus 7, I'm going to write 5x plus 7 in the parentheses. And then you proceed to simplify the expression. There's nothing in front of the parentheses keeping there, so we can erase them or just pretend they are not there. And then in the numerator, we have like terms, 7 and negative 7. They cancel. That leaves us 5x on top of 5. Can you cancel the 5s? Yes. Remember the rule for canceling in a fraction. You can only cancel parts of multiplication problems. The numerator is a multiplication problem. The denominator is just a single term, so it's good to go. But if you force me to show that it's part of a multiplication problem, I'll put 5 times 1 and go, C. Anyway, the 5's cancel, and we're left with the x, which is what we wanted. So what this means is, whatever the f function does to the x and turns it into a different answer, the g function will undo it and give us back the x that we started with. 1 down, 4 to go. Now let's check the reverse composition, the other composition, f of g of x. And it doesn't matter which one you do first. So to calculate f of g of x, that is f of g of x. And honestly, you don't even have to write this if you understand that that's what this means. Because the setup is the same each time. You write the outer function with parentheses instead of x's. So we're going to write 5x plus 7, but replace the x with a parentheses, or a set of parentheses. And then fill in those parentheses with the inner function. The inner function is g of x, so x minus 7 over 5 will go inside the parentheses. But if you're on your game, you can actually start with this from here. Just remember which is the outer, which is the inner, and which one does what. All right, let's simplify this. Let's see, please excuse my dear Aunt Sally. Go inside the parentheses, I really can't do anything. So going outside the parentheses, we have multiplication and addition. Multiplication takes precedence. Can we cancel the 5s? Yes. The 5 on the left is part of a multiplication problem. And again, the 5 on the bottom, if you force me to, I can write as 1 times 5 and make it part of the multiplication problem. But the 5s do cancel, leaving an x minus 7 in parentheses plus a 7. And at this point, the parentheses are really no longer necessary. There's nothing in front of them. So we can erase them or just ignore them. The 7s cancel, we're left with an x, and that's what we wanted. But we're not out of the woods yet. In many problems, this would be sufficient. In fact, I think in some of these homework problems, they don't even ask you about domains and ranges. But I'm going to, because in the next example, you'll see why they are important. So let's start with the domain and range. Oh, wait a minute, how are we going to get the domains and ranges off of these? Well, the domains are easy. If you go back to the previous series of videos and watch the first one, this is a polynomial function. Its domain is all real numbers. And although this doesn't look like a polynomial function, it is. In fact, it's a linear function, because if I split this into 2 fractions, I can write it as 1/5 x minus 7/5. So not only is it a linear function, I know its slope and y-intercept. So how can we get the domain and range off of a function when all we've talked about is pulling its domain out? Answer, sketch its graph. We're going to do 3 and 4 simultaneously, because we're going to find each function's domain and range and see if we have the correct equalities. So let's start with f of x equals 5x plus 7. What do you know about this graph? It's a line, its slope is 5, its y-intercept is 7. Now, our graphs don't have to be super accurate, they just need to be good enough to be able to determine the domain and range. This graph would have a y-intercept of 7, the slope would be 5, so we could run 1 and rise 5, and put a dot up there somewhere. So we would get a fairly steep, but not quite vertical line. So what is the domain of f of x? Well, this line goes forever left and right, so it's negative infinity to infinity. But we already knew that because it was a polynomial function. All polynomial functions' domains are this. But what's the range? Well, from a graph, the range is the lowest to the highest. This goes forever down and forever up, so the range is also negative infinity to infinity. So this means we can put in any number, but we can also get out any number from f of x. And the same thing for g of x, and even though the graph of the function, the function is a little junkier with all these fractions, we can still get a rough idea of what this graph would look like. For example, the y-intercept would be negative 7/5, which would be down here somewhere. And interpreting the slope as rise over run, we could rise 1 and run 5, and that would put a dot over here. And we would get a line that's not nearly as steep as the previous one, which makes sense since its slope is much less than the previous line's slope. So what's the domain and range of this graph? Well, doesn't it go forever left and right, making its domain negative infinity, comma infinity? And although it's slow, doesn't it go forever down and forever up, making its range negative infinity, comma infinity? Do we have the correct equalities? Well, everything is exactly the same, so yes, but specifically, we have to compare the domain of one with the range of the other. Those two match. And we have to compare the domain of the other with the range of the first, and those two match. So what this means is that whatever goes into one function is capable of coming out of the other. Whatever goes into f is capable of coming out of g. Whatever goes into g is capable of coming out of f. So all 4 criteria are satisfied. So the answer to this question is yes, these are inverse functions. Okay, I'm not going to write it on here because I'm out of space, but that's okay. So they are inverse functions. Oh, before I shut down this video, I do want to say one more thing about notation. So I am going to erase this. Since it's a video, if you missed it, you can pause it and go back and write down what you want. But since the answer is yes, There's a notation specifically to say that one function is the inverse of another. So yes, they are inverses. And the notation goes something like this. F of x is defined to be 5x plus 7 in this problem. To explicitly show that g of x is its inverse, instead of writing g of x, we could write the following. F with what looks like a -1 power of x equals x minus 7 over 5. This is not an exponent. This is a symbol that means inverse. So the way you would read this, you could say f inverse of x, or you could say the inverse of f of x. So you could say either one. You could say f inverse of x, or you could say the inverse of f of x. But it's explicitly stating that I am the inverse of somebody else. I am the inverse of you. And similarly, if this was g of x, we can say that g inverse of x is 5x plus 7. So if you ever see a function with a what looks like a -1 power, it's not. It's a symbol saying that I am the inverse of another function. I am the inverse of some function g of x. I am the inverse of some function f of x.